All right, good evening everyone. If someone can switch to my, is there, okay. Still function. Yes. All right, good evening again. Happy to see all of you turn out in large numbers, especially given the horrible weather today. Sometimes it is really better to be in other parts of the Dutch kingdom than Leiden. I'm going to talk about the Gaia mission. This was the launch logo that was to the rocket 4 years ago when we had the launch. There's in fact a few people in this room who were there pressing the button for the rocket to launch, and I should thank them again for making this a big success. Just to mention that we did our first catalog release from this mission, the first data release last year, and there have already been over 500 publications based on that, and you'll hear the results of one of those later in the second talk. Okay, so what is Gaia about? Well, let's first have a look about 1 million years from now, 1 million years into the future, to see what's going to happen to our skies. Pay close attention to this particular star. We're 1 million years and time is running. And this star is actually approaching us. So it's getting brighter and it's starting to move faster and faster across the sky. And in fact, this star, in about 1.5 million years from now, will be just about the brightest star in the sky, which is the brightest star at the moment. Now Gaia can measure this type of thing. So how do we know this? How do we know that this star is going to come at us and come very close? It's going to come so close, in fact, that it will pass through the so-called Oort cloud, which is a repository of comets around the sun, and this may cause problems. We may get a shower of comets on the Earth. It's nothing for you to worry about now. It's 1 million years into the future. So how do we know this? You need to know two things. You need to know where the star is right now, so we need to know at what distance it is. We need to know how it's moving, where is it going. Otherwise we can't predict that it's going to come very close to our solar system. So here's how we measure where stars are, so how far away they are. So here's us on the Earth going around the sun, and we're interested in the distance to this star. And as we move around the sun, the line of sight to the star is obviously changing. And this reflects itself on the sky as a motion of the star against the background stars. Yeah, this is just a reflection of us going around the sun, and then the star appears to make a little circle on the sky. So I'll let this animation run again. So here the star is close, so the line of sight changes a lot, and that means that the star is moving in a large circle on the sky. So that means it's close to us. It means it has a large parallax in the words that we use in science. And then when you move the star further away, you can clearly see that this circle gets a lot smaller. Now, by measuring the size of the circle, we can directly infer what the distance is to the star, because we know the distance between the Earth and the Sun very well. And this is the only way, in fact, that we have of directly measuring distances to stars and thereby calibrating all kinds of other distance measurements that we use in astronomy. Imagine that this star is not standing still, but moving across with respect to the Sun. Then the net motion is shown over here. So the star, on average, moves in a certain direction on the sky. That's because it's not standing still in space, but it's moving with respect to us. And at the same time, you see that it makes this little dance. It's going back and forth. And again, that's just a reflection of the fact that we are sitting on the Earth and going around the sun and constantly changing our perspective on the star. Now let me take out my one little prop. These motions that the star makes are tiny. I have here a euro coin, and the size of the motion you see over there, which takes place over the course of about 3 years, would be the same as this euro coin if I put it on top of the Burj Khalifa in Dubai, about 5,000 kilometers from here. And if you can still see this euro coin, that's the size of the movement that the star makes. And you have to wait for a few years for it to move, right? So next time you're asked what does Brown actually do for a living? Well, I literally stare at the stars all the time and wait for them to move. Now the message of this is that the sky is not static, the sky is moving. It's moving because we are moving around the sun, and it's moving because the stars are moving in space. This is what the sky would look like if you had eyes that could see that euro coin over in Dubai. Here's the constellation of the Big Dipper, and the stars are going back and forth. And you know by now that this is because we are going around the sun. At the same time, you see that stars are also moving across the image. Yes, and you see that the shape of the Big Dipper is... Here's what we know it like now. And you see how it changes over the course of time. And again, this is because stars are moving with respect to the sun through space. So the sky is not static. If you wait long enough, many thousands of years, many millions of years, all the constellations will change and be unrecognizable to us in the future. Okay, so as I mentioned, we did so the task of Gaia, this satellite, is to measure all these motions of the stars. And I mentioned that this Euro coin 5,000 kilometers away, which Gaia can easily see, Gaia can in fact measure 100 times more accurately. It can see the Euro coin all the way on the moon. Last year we did a first release of a catalog of the sky. So we measured these positions over the course of time for 1 billion stars. And here you see the resulting map of the sky. So this is the Milky Way band, and this is the entire night sky. And that was the main product that we put out last year. Big map of the sky, but measured with accuracy that is unprecedented. And for a small subset of the stars, we also measured their distance and the way they move through space. And we did that with this satellite. Briefly say hi to Gaia. I won't bother you with all the details of this mission. That will take another talk. Now, we put out mainly a sky map last year, and you can wonder, well, what's the point of putting out a billion-star catalog with just positions, without yet the distances and motions? Well, let's take an example from a lot closer to home. This is the moon Triton, which goes around Neptune. And on October 5 this year, Triton was going to pass in front of a star. If the star disappears behind Triton, you'll get a small shadow on the Earth. And by measuring the light of the star, you can see that it dips as the shadow passes over us, and the star becomes then bright again. Now, the interesting thing about Triton is that it has an atmosphere, a quite substantial atmosphere. And it means that if the star is exactly behind Triton here in the middle, the light gets refracted around by the atmosphere, and you actually get what is called the central flash. It becomes a little bit brighter right in the middle of the occultation, right in the middle of the shadow. Now, this is very interesting to measure because we can learn a lot about the atmosphere of Triton itself. But you need to know very precisely where to put your telescope. Otherwise, you'll miss this central flash, and all the excitement is lost. So what do we do to make predictions? We need to know where the stars are, so we can predict that they will be actually occulted by, for example, Triton. And we also need to know exactly where Triton is going to be, so that we know that the alignment is correct, and we can pinpoint exactly where we should be on Earth to observe this. Now, this was a prediction that was done earlier in the year of where exactly the central point of this shadow would pass over the Earth. The shadow itself is quite large, but the central part where you can actually see that central flash was predicted to pass over Europe, mainly more or less over the south of France. So everybody was ready to put their telescopes there. But then they said, well, we're not entirely happy with the predictions. So let's ask the Gaia team if they can already give us a couple of positions of stars and their motions and parallaxes, so the motion caused by the motion of the Earth around the Sun, so that we can improve our predictions. Because if you want to predict where a star is exactly on a particular moment, meaning a particular minute in time, you need to know both the way it moves and both the distance to the star. So we gave them this preliminary data, which we're only supposed to release actually next year in April, but we thought this was important enough that we gave them the data for a few stars. And we also gave them data to improve the predictions of where Triton would be. And then the prediction shifted. So it went from the south of France, basically sort of passing through Portugal and Spain. I'll flash it back. It's a 300-kilometer shift, yeah, this difference in knowing exactly where a star is and only knowing it approximately. So now, of course, the test comes on October 5. Let's see if our prediction was correct. So here's a movie. This is Neptune, this is Triton, this is a star. It passes behind Neptune and you quickly start blipping. Yeah, so the star is dimmed a little bit. I'll just let it pass again. Here's the star passing behind Triton. It becomes a little bit dimmer. This is a measurement from the south of France. Damn, there's a central flash there. And we said we shouldn't go to the south of France. It's much better to be in Portugal. This is the measurement from Portugal. Look at the central flash now. Much better. So we were very happy, right? It was also our reputation on the line, but the predictions were exactly right, and it's a great validation of the enormous precision that Gaia achieves with its measurement of star positions. Okay, let's go back now to the 3D aspect of all of this, the fact that we can measure where stars are in space and how they are moving through space. So first I'll show you a 3D movie which was made with a piece of software called Gaia Sky, which you can actually download and use yourself to play with the Gaia data. And what we'll do is, this is the area on the sky around the Orion constellation. This is Orion. Here is the head of Taurus. And this here is the Pleiades cluster. And what we're going to do is we're going to fly straight towards Taurus and then veer off to the right to the Pleiades cluster. And we can do this now because we know exactly what space looks like in 3D. We've pinpointed where the stars are. So there's Gaia getting ready to fly towards Taurus, which is over here. This is Orion. Now wait for it. This is a long distance we have to fly, so not much will happen in the beginning. It will take a while before we've accelerated sufficiently to start seeing stars move. This here, the Orion constellation, if you look closely throughout the movie, you'll see it change shape. And that's not because the stars are moving, but because we are changing perspective with respect to this constellation. As I said, you have to be patient. Here's something moving already, and now we're getting there. Now our spacecraft has accelerated sufficiently that we can see actually things passing by. Here's Aldebaran, one of the brightest stars in the sky, the brightest star in Taurus. It's very close, so it's already behind us now. And you can see how the shape of Orion has distorted. Yeah, so the torso of the bear hunter is basically gone. The belt is starting to distort. Now we're flying through the Taurus constellation. This is actually a star cluster called the Hyades. Going right through it, going off to the right, and now we're moving towards the Pleiades, the Seven Sisters, another famous star cluster. Right, so this kind of game you can now play because we know exactly where stars are in space. This is real measurements. This is not some simulation. This is really where they are hanging out in space. Of course, this is an animation that was made. We can't yet do this with a spacecraft, but we can actually imagine what it's like. Now, another neat thing we can do, this is a map seen from above the galactic plane, near the sun. The sun is somewhere over here. And we can look for concentrations of stars and draw sort of a surface around them to indicate where these concentrations are. In this case, we only look at concentrations of very young stars. And young in astronomical terms means a few million years old, maybe up to 10, 20 million years old. These stars tend to be very blue and very bright. So they're actually quite conspicuous in the night sky, a lot of them, and they're distributed unevenly through space. So it's important to map them by making these sorts of constructs where you put basically a surface around the concentration of stars, and then you can study how they are distributed in space. Now, if I set this in motion, we can zoom out. So the sun is somewhere over here. And the colors indicate increasing concentration levels of stars. So in the pinkish is where the most stars are located. And as we zoom out, you can notice that there's a huge concentration of young stars over here. That's towards the constellation of Scorpio and Centaurus. We know that there's a group of young stars just having formed. Orion is somewhere over here. We have one of the Orion experts actually among the people from the observatory here tonight. You can ask her more later. And if you look closely now, you see that in this region around the sun, there seems to be a bit of a hole. There's lots of young stars all around us, but not directly near the sun. And this is indeed the case. We are living in a so-called local bubble with a lack of stars. And this can be mapped now very nicely with the data from Gaia. And in fact, what you can do is you can make this into a 3D rendering like this. And this is you can 3D print this. And I have this with me. And during the intermission, if you like, you can come to me and admire this, and I'll explain a bit more about it. But we also have the maker of it here, Kevin, and he will be even much better able to explain in all the details of how you can actually make these kinds of 3D renderings and 3D prints. It's really quite neat, and we can do this thanks to the measurements of Gaia. Okay, just a few credits to end up. So I didn't do all the visualizations myself, of course. So some of the movies by Jos de Bruyne, the Gaia Sky movies by Tony Sagrista and Stefan Jordan. I just mentioned the role of Kevin. I have here some links. I'm not going to read them out, but you can come and ask me later. Some of the code is available online, and in particular Gaia Sky is something that you can play around with yourself. And then while I take questions, I'll leave you with the future of this part of the sky. This is again is the Orion constellation. Over here is the Taurus constellation, and I'll set everything in motion. You'll see the proper motions of the stars, also a little bit of a parallax, and you can see slowly how the sky is changing over the course of time. I think this is a very pleasing movie. It's like an aquarium. You can sit and stare at it for hours and completely relax. Thank you.